All right, number 9 is about a grocery store receiving deliveries of corn from 2 farms, one in Iowa and one in Ohio. Both farms produce ears of corn with a mean weight of 1.26 pounds. So let's start writing that out. So we'll start out with Ohio. And the mean for Ohio is 1.26. Standard deviation of the weights of ears of corn from the farm in Ohio is 0.01 pounds greater than that from the farm in Iowa. That's a comparative value, so let's leave that for the moment. So 1.26 pounds, sigma we'll just kind of leave for the time being. And then Iowa was the same. Mu was 1.26 pounds. Okay, now the standard deviation, let's read that again. Standard deviation of the weights of the ears of corn from the farm in Ohio is 0.01 pounds greater than that from the farm in Iowa. So they don't really say anything about the farm in Iowa, so let's just call that X pounds. Remember assigning variables like that in Algebra 1 is the same kind of thing. All right. So for Ohio, it's the same X, only 0.01 pounds more. So we can just say that's X plus 0.01 pounds. All right. So a randomly selected ear of corn from the farm in Iowa weighed 1.39. So we'll just call that a measurement, an X, 1.39 pounds. So this is Iowa. Which has a standardized score of 1.645. Right, a standardized score is a z-score. So that's 1.645. Okay? For the distribution of weights for Iowa corn. If an ear of corn from the farm in Ohio, so let's build a section over here for Ohio, also weighs 1.39 pounds, that's another observation. How many standard deviations from the mean is the weight with respect to the Ohio distribution? All right, standard deviations, the number of standard deviations from the mean, again, is a z-score, right? So that's what we're trying to find. See, standard deviations, all through choices A through E. So a standard deviation is how far away a value is from the mean of a distribution. All right, so we do have a lot going for us for Iowa. So that's where we're going to start. We know X, we know mu. We know X, we know mu for Iowa. Sigma we don't know, but we do know the z-score. Now finding z-scores, you're not limited to normal curves. You can find a z-score in any distribution. So we're just going to do, the x minus mu over sigma equals z. That calculation, so here it's 1.39 minus 1.26. We don't know the standard deviation, that'll be x. But we do know that that will give you 1.645 for a z-score. All right, now we just need to solve for x, which will be very useful. All right, so multiply each side by x, that'll clear that out. 1.39 minus 1.26 is 0.13 equals 1.645x. And we can just solve for x. 1.645 divided into both. All right, so we'll end up with x equaling 0.07027. I believe I've left a number out. Let me put that number in. 0.079, we'll make that a 9, 027. All right, and that's your standard deviation, so that's going to be in pounds. Okay? All right, so if we know that this is 0.079027, if we add 0.01 to it, we should be in pretty good shape. So sigma here is going to be 0.079027 plus 0.01, which is 0.089027. All right, so we know sigma, we know x, and we know mu, so we should be able to just put that into the same kind of equation, 1.39 minus 1.26 divided by 0.089027, and that will give us the z-score, or the number of standard deviations above the mean, which is about 1.46. So that's how you get your answer for number 9. All right, number 10. For me, this one was probably the toughest one out of all 40. I mean, it's different for everybody, but there's a lot in it, and if you're really not recognizing what's here, it can be a real monster. Now, we did do a problem sort of like this one, that it was, well, not that long ago, but it's one of those things that I think a lot of people just looked at and just shook their head, and didn't really get any experience with it, so all of a sudden you're faced with something like it again, and it's just as alien as the first time. But let's give it a go. So the the distribution of numbers of hours worked by volunteers last year at a large hospital is approximately normal. So let's start writing that out. X is approximately normal with a mean of 80 and a standard deviation of 7, so that's a good start. And we can even build a curve. Never hurts. Help to visualize, so we'll center that at 80. All right, volunteers in the top 20% of hours worked will receive a certificate of merit. All right, so let's just kind of section this off, and this will be like your top 20, so that'll be 0.2. And below that will be 0.8. I think that may be important. If a volunteer from last year is selected at random, which of the following is closest to the probability? All right, so we're looking for probability, and that makes sense. Look at these answers. They look like probabilities. That the volunteer selected will receive a certificate of merit given that the number of hours the volunteer worked is less than 90. All right, the major thing here to not miss is this. The given that. This is conditional, right? So remember what the formula for conditional is, or was. All right, the probability of B given that A occurs is the probability of A and B divided by the probability of whatever this is. That's the probability of A. All right, so we've got two things that are being interacted here. Winning a certificate of merit, or earning one, and let's see, working less than 90 hours. So given that the number of hours worked is less than 90, I'm going to let that be my event A. So it'll show up here and it'll show up here. So A is the event of work less than 90 hours. And it's really important to define these things. It makes things a whole lot easier. So that's going to make event B be the event that a person receives, a volunteer receives a certificate. And I'll just abbreviate that. Well, we know that probability. The probability of B is going to be 0.2. I don't know that we'll need it, but we sure do know it. So we need to figure out the probability of A. Definitely we need that because it's in your denominator right there. All right, the probability of A is, we've already defined it as working less than 90 hours. So let's just for grins locate 90 somewhere up here. And so that would be all of this. Right, working less than 90. So we can figure that out with standard normal calculations. So the probability that X is less than 90 is the same as the probability that z is less than 90 minus 80 over 7. And that's just a normal CDF. So normal CDF. And we're going from what? Negative infinity here. So we'll just put negative 1,000 up to 90, mean of 80, standard deviation of 7. And that will give you, let me look at my trusty cheat sheet, 0.923436. That is your probability of A. So 0.923436. Okay, good. We're looking for this. We know this, right? So we need to figure out the probability of A and B. Now don't assume you can just multiply those two together. You can't, because you're assuming that A and B are two independent events. And we don't know that that's a fact. We just don't know that. So I'm going to refer you to something that you might not have considered, or you might not normally consider. But remember Venn diagrams from way, 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 way back? All right, let's call this A, let's call this B. You know where they overlap, like right here? That's A and B, right? So if we can find the overlap between this blue and this red, which would be, if I put a different color to it, would be everything right here, right? Then we would know the probability of A and B, because that's where the two overlap, just like here. All right, so what we can do is just, let's just write it out here. All right, let's just take the probability of A, that's your, all of this red, that's 0.923436, and take out everything from here down, which is 0.8. Remember the 0.8 from before? So minus 0.8, and that'll give you 0.123436. So that is your probability of A and B. So now we know this. So this over this should give us this conditional. So let's figure that out. This will be 0.123436, probability of A and B, over the probability of A, 0.923436, and that will give you 0.133671, or approximately 0.134. So there it is. We figured it out. Let's move on to the next thing. All right, next up is number 17. Number 17 is a really good one. It's a random variable question, and specifically it's about combining random variables with all the little nuance and all the little rules that go with it. And on top of that, it's a normal random variable. So let's check it out. So Sean and Evan are college roommates who have part-time jobs as servers in restaurants. Distribution of Sean's weekly income is approximately normal, so we can kind of put that down. So that we'll call him X, and that'll be approximately normal with a mean of $225 and a standard deviation of 25. And then we've got Evan, and his distribution, we'll just call him Y, random variable Y, is also approximately normal with a mean of 240 and a standard deviation of 15. All right, if we're going to combine these two things and they're both sitting at normal, then the combination will also be normal. So assuming their weekly incomes are independent, which of the following is the closest to the probability that Sean will have a greater income than Evan? All right, well, if we're trying to see who's got more or less, we need to sort of base this on a difference. So let's just say this will be Sean minus Evan, or that would be X minus Y. So we need the new distribution for x minus y. All right? So, right. So let's go ahead and just say that that's going to be approximately normal. And the rules for means is that we can just subtract the 2. So this will be 225 minus 240, which will be negative 15. And that's okay. It's just a point estimate. So that'll be negative 15. And now we need the new standard deviation. All right, we're going to take the two old ones. And remember, those never combine with subtraction. Spread never diminishes. It either stays the same or grows. And you just can't add the two together. So what we have to do is convert to variance. So let's just say that the variance of x minus y is going to be the square root. Oh, check that. Let me go back. That's just going to be 25 squared plus 15 squared. And then to get the standard deviation of that, we're just going to take the square root of that. Okay, so that's going to be the square root of 25 squared plus 15 squared. And that will give us, 29.1584. All right, so here we go. 25.1584. All right, so this distribution is going to be normal, approximately, and it's going to be centered at negative 15. Okay, well, we're interested in where Sean will have a greater income than Evan, right? So where they would have the same income would be where the difference is 0. And anything beyond that is going to be where Sean is greater than. So this will be a relatively small probability. Relatively, all right? So we can just go ahead and do the probability, and let's just say that this will be that x minus y is greater than 0. All right, that's equal to the probability that z is greater than, all right, 0 minus a negative 15. So it's x minus mu over sigma divided by 20. Oh, I have a mistake here. Let's go ahead and change that to a 9. Just have a little bit of a goof up. I wrote 20, I had 29 here and wrote 25. There's your old man coming out. All right, so this is 29.1584. And I'm just going to go ahead and go straight to normal CDF for this. All right, and this is going to go from 0 to infinity, right? Infinity would be up here. So I'm just going to pick a big number, and then the mean is negative 15, and the standard deviation is 29.1584. And that will give you 0.30345. And that looks a lot like letter D. So there is your answer for number 17. All right, so on to number 28. Kind of a probability question, although it's a little bit deceptive. You kind of have to pick out what's going on here. So you got a die used in a certain board game has 8 faces, of which 3 are red, 3 are yellow, and 2 are blue. Each face is equally likely to land face up when the die is tossed. In the game, a player tosses the die until blue lands face up, and the number of tosses before the blue lands face up is counted. For example, now this is one of those things that is a little bit this is a little bit misleading. They give you an example, but I believe that they really want you to work through this in a theoretical basis, and I'll go a little more into that. So for example, a player who tosses the sequence shown in the following table has tossed the die 3 times before a blue lands face up. All right, so this is 1 out of 4, right? Yellow, yellow, red, and then finally a blue. So 1 out of 4. All right. So, but let's just go back and review the overall probability of getting a blue. So you've got 8 faces, 3, 6, and 8. 2 of them are blue. So the probability that any toss will give you a blue is 2 out of 8 or 1 out of 4. You can also say 0.25. So what is the probability that a player will toss the die at least 2 times before blue lands face up? All right. It's easy to miss the fact that what you're doing is looking for the first success. You either get a blue or you don't. The probability of getting a blue is constant, 0.25, and all of your tosses are independent. This is going to be geometric. And since it's at least, this will be a geometric CDF. All right, so at least 2 times before is an important word too, because that means it can happen at the 3rd, 4th, 5th, or anything beyond that. All right, so really when you set this up, you're going to have a geomet CDF. All right, and your probability of success is 0.025. You want your first success by the 3rd one, and it can go on forever. So I just put a big number here to soak up the rest of the probability, and you get 0.5625, which is here. All right, so it's a basic geometric problem. We're usually used to getting these things as binomial, but here it is geometric. So that's that one. On to the next. All right, next one that was requested was number 35. And this was one of the ones that I kind of gave to you because this particular subject is not going to be on the AP exam. This is inference for regression, and the College Board just jettisoned that. Now, we did talk about it a little bit. I tried to make sure that we got a complete presentation of the entire course, but we did kind of shortcut this a little bit. It's not really something that you need, and I did give you the answer for it. But what you've got here is, well, let's just read it. A student working on a physics project investigated the relationship between the speed and the height of roller coasters. The student collected data on the maximum speed in miles per hour and the maximum height in feet for a random sample of 21 roller coasters with the intent of testing the slope of the linear relationship between maximum speed and maximum height. However, based on the residual plot shown, the conditions for such a test might not be met. All right, you probably could have answered this one, just by guessing, with some thinking about it. These are all what I mentioned as being ways to verify your conditions for a linear regression t-test or interval. And I think the most obvious one that's violated is this one here. The variance of the response variable is constant for all values of the explanatory variable. What they're saying here is that this should be a fairly constant spread, but if you look at it, it is trumpeting out, and the spread is increasing throughout the residual plot. So this guy is violated. That's the one that has been violated. So E is the right choice. So on to the next one. All right, here's the last one that I got a request for an explanation on. I didn't get too many requests. Some of you may be tied up with other things. I know that calculus, for example, had a big mock exam that probably took away a lot of your time during the week. Last week, that is. So if you have more time to devote to stats now, or depending on what your AP exam situation is like, just contact me, and one way or another I'll get an explanation to you. But anyway, so 37 here, high school students from track teams in the state participated in a training program to improve running times. Before the training, the mean running time for the students to run a mile was 402 seconds with a standard deviation of 40 seconds. So we can kind of record that. Let's see. So we'll just go with before. And we'll just call that random variable x. And so this will give you the mean. It's not actually normal. We're not told that they're normal, so that kind of doesn't matter. So mu is going to be for this group 402 seconds, and a standard deviation equal to 40 seconds. Okay. After completing the program, the mean running time for the students to run a mile was 368 seconds, so we'll call that y. And so the mean did drop. That's 368. And a standard deviation of 30. All right, so let's see what they want. Let x represent the running time of a randomly selected student before training, and let y represent the running time of the same student after training. Which of the following is true about the distribution of x minus y? All right, the difference here, we can just say that the mean of x minus y is just the difference in the mean. So that's going to be 402 minus 368. So let's see, that's going to be 34. All right, so we have that here. We have that here. Let's see, we have that here. And we don't have it on some of the other ones. So what about the combination of the two standard deviations? Now you might think, okay, we can square that and square that, add them up and take the square root and get the combined standard deviations. But you would not be correct, because that is only going to be a valid thing to do if x and y are independent. And the thing about this is that x and y really aren't independent. So that's kind of out. Let me just put it to you this way. We're talking about a mean running time for students. Well, within that is going to be individual running times that have been averaged up. So if you have your fastest runner, just in general, wouldn't you think that that fastest runner would then be the fastest runner after completing the program, and the slowest runner would be among the slowest runners after completing the program? All right, if you can make that kind of a judgment, then those two variables, before and after, are really not independent. And I did go and look this up, because I looked through the notes that I had taught you, and I think I may have thrown it out there quickly, but not enough to really emphasize it. So here's the online textbook, and here is kind of your summary rules for combining random variables. And like, the mean of the sum of two random variables is the sum of the mean. The mean of the difference of two random variables is the difference of the means. Here's what we need, the third bulleted point. If the random variables are independent, then the variance of their sum or difference is always the sum of the variances. Okay, so that's like a condition that you have to meet. And we did not meet that particular one. I'm going to come back to this in a minute. So if you read through these things, x and the variables x and y are not independent. Therefore, the mean is 34 seconds. You can still get the mean. The independence condition does not apply to the mean. Standard deviation cannot be determined. So this is your answer. All right? So that's the explanation for that. And just as I was reading this, I'll go back to this page. They made a connection between, combining standard deviations to the Pythagorean theorem. And I thought, who knew? When you try to find the side of a triangle, it's always a squared plus b squared equals c squared, right? It's not a plus b equals c. Similarly, you have to square a standard deviation to variance and then square for a different random variable that standard deviation to variance, add them up and take the square root just the way you would finding a side in the Pythagorean theorem. So interesting. After all these years of using this textbook, I never read that. So anyway, that concludes our video on working through some of the things with your multiple choice practice test. So stay in touch with me and keep asking questions as we head into the AP exam.